Hello everyone, my name is Mohammad Hodeai and I'm a graduate student at Tennessee State University. Our research is focused on highly stretchable and tough pantograph-inspired lattice metamaterial. The motivation behind the research is that superelasticity is useful in many engineering applications, for example, searchable sensors and structures that can dissipate energy without damage. However, increasing the elastic limit of material usually reduce stiffness and strength. Also, achieving this behavior is not easy. Several structural mechanisms have been explored to achieve large searchability in engineering materials. One of them is out-of-plane deformation, which can reach up to more than 200%. However, out-of-plane deformation can introduce instability and geometric nonlinearity. An alternative is in-plane deformation, where searchability is achieved through rotation of structural members while remaining with the plane of structure. The mechanics are commonly found in pantograph type lattice, and because deformation occurs primarily through controlled rotation rather than buckling, the structure can provide large searchability while maintaining structural stability. To address the trade-off between searchability and the stiffness, we propose lattice architecture inspired by pantograph mechanics. In this design, pantograph motifs are embedded in polygonal lattice template. As you see here, this is a hexagon shape, and this is a diamond shape. And they are connected through cylinders. You see a pantograph-inspired lattice structure. The structure is constructed by embedding, as I said, the connectors within the lattice template. Different geometry can be assumed, such as hexagon, triangle, diamond, and also hybrid is possible. We are interested to do analytical screening using geometry compatibility and then use the micromechanics model and finite element model analysis and experiment to validate that. And the reason actually behind this that we are interested to do analytical screening is to avoid the tedious process of experiment and finite element model before know which model really is really good for us. So here you see RVE or representative volume element of the diamond shape. To analyze the deformation mechanism of lattice, we start by defining these RVEs. The RVE actually is the smallest repeating unit of lattice that can be repeated to generate the entire structure. Using geometry compatibility, we relate the rotation of the struts. This is the struts. Sorry, excuse me. Rotation of the strut to the macroscopic deformation of the lattice. This allows us to derive a relationship between the lattice geometry and the resulting strain and effective Poisson ratios. The key point is that the deformation of the lattice is governed primarily by geometry rather than material deformation. Here is another example for the hexagon shape. You see here the red line represents the RVE for the structure, and the same process we need to do for each single configuration that we assume. So to explain the analytical screening and how do we screen different lattice geometry before do a finite element or experiment. We assume that the strut R behaves as a rigid member, and as a result, the total deformation would be the result of displacement and rotation of the cylinder. So therefore, the total displacement is described with delta R, which come from the twisting of the cylinder, and the delta SP, which come from the shear and bending of this cylinder. The energy equations equals is a result of deformation, the rotational deformation, and the shear and bending terms of that cylinder. The shear bending terms is derived from the Timoshenko beam, and you can see the stiffness and the phi, and also the torsional, the KT GJ over L, the stiffness, the torsional stiffness, and our unknown is delta R and delta SP, which we are interested to find. And the total energy, the capital U, we assume to be equal to the U critical of the yielding elastic limit of the same material for the dog bone shape which we obtain in the experiment, because we say that the total energy that this material needs to reach the elastic limit, because the material is the same, those elastic limits also are the same. So so we replace that energy to reach that elastic limit equal to U critical that we obtained from the experiment on a dog bone sample. And then, because the rotation and the shear and bending are not in the same direction, then we are interested to translate and transform this rotation to the longitudinal direction. We convert that rotation to the longitudinal, and we came up with the equivalent stiffness, so we can represent our model as two springs in series. This helps us to come up with the second equation, because when these two springs is in series, the deformation could be different, but the force inside should be the same. So we came up with the second equation. By solving the first and second equation simultaneously, we can obtain the delta R and delta shear and bending and sum them up in the longitudinal direction and come up with the delta critical, which is the delta corresponding to the U for the elastic limit. And then as a result, we, before do any finite element or experiment, we can see which of those configuration will give us the best possible with a given U, which is defined for a material, which of those configuration can give us the maximum delta. Then we know which configuration would be the best for us. And then also this slide also this represent how macro-micro deformation mapping is established and how the micro-macro energy equivalence is established, as I explained in previous slides. So I want to also show you a video of the samples that we have done experimentally. This is for one of our pantographs, samples that we have done in the lab. And I'm going to fast forward this, and it goes to uh, hopefully failure. You see how searchable is this configuration is. Yeah, you see the failure in the members, and it's been the sample is failed.